Assalamualaikum and hi everyone. We are from Group 4. We present to you guys the solution for SCL reanalysis that consists of 6 questions. So without wasting our time, we will give to you guys the solution for task number 1.
So let's start with task 1. Before that, let me introduce myself first. My name is Nurfahima Nabiha binti Muhammad Sofyan and my matrix number is 2022970. So I will explain and discuss task 1. The question is, prove that S equal to 1 over n equal to 1 until infinity is contractive by given definition 1. So how to solve this question? So I will use the definition to find the R or the constant that between 0 and 1. So the solution for this question is, suppose that n is element of natural number, then modulus 1 over n plus 1 minus 1 over n less than or equal to R modulus 1 over n minus 1 over n minus 1. So let's make R has a subject, then we get modulus n minus 1 over n plus 1. So let's substitute n equal to 2, then we will get 1 over 3, which is less than 1. Then we substitute n equal to 3, we will get 1 over 2, which is also less than 1. So since R is more than 0 and less than 1, so this sequence is contractive. So let's proceed to task 2. The question is, prove that S equal to square root n equal to 1 until infinity is not contractive. So the solution for this question is like task 1, but this time we must to find R or a constant is not between 0 and 1. So the solution for this question is, suppose that n is element of natural number, then modulus square root n plus 1 minus square root n less than equal to R modulus square root n minus square root n minus 1. So let's make R as a subject. So we will get the answer is 1 over square root n plus 1 plus square root n times square root n minus square root n minus 1. So next, limit n to infinity, 1 over square root n plus 1 plus square root n times square root n minus square root n minus 1 less than R. So limit n to infinity, we will get 1 over infinity. So the answer is 0. So since R is equal to 0, the sequence is not contractive.
Alright, now let's move on to task 3. First of all, let me introduce myself first. My name is Nur Izzatul Akma binti Abu Hasan As'ari with matric number 200319. So task 3 requires us to prove lemma 1, which is if S equal to Sn from n equal to 1 until infinity is a contractive sequence, then there exists a positive number R from 0 to 1 such that modulus Sn plus 1 minus Sn is less than or equal to R to the power of n minus 1 modulus S2 minus S1 for n greater than 1. So we know that from task 1, a sequence is contractive if there exists a constant R such that R from 0 to 1 for modulus Sn plus 2 minus Sn plus 1 less than or equal to R modulus Sn plus 1 minus Sn for n greater than 1. So firstly, by assuming m is greater than n, we can write as modulus Sm minus Sn it is equal to modulus Sm minus Sm minus 1 plus Sm minus 1 minus Sm minus 2 plus until Sn plus 1 minus Sn. We can separate the equation with a modulus such that modulus Sm minus Sn is less than or equal to modulus Sm minus Sm minus 1 plus modulus Sm minus 1 minus Sm minus 2 plus until modulus Sn plus 1 minus Sn. So notice the pattern here. Modulus Sn plus 2 minus Sn plus 1 is less than or greater or equal to R modulus Sn plus 1 minus Sn. It is also less than or equal to R square modulus Sn minus Sn minus 1. Modulus Sn plus 2 minus Sn plus 1 is also less than or equal to R cubed modulus Sn minus 1 minus Sn minus 2. So here we can see that the lesser the number of n, the number of R will be double. So since we want modulus S2 minus S1, but we don't know what number of n that represent for S2 and S1, so we will just put R to the power of n. So from the previous pattern, we get that modulus Sn plus 2 minus Sn plus 1 is less than or equal to R to the power of n modulus S2 minus S1. So since the question asks for R to the power of n minus 1, so now we will replace n by n minus 1 to the equation above. So now we will get modulus Sn minus 1 plus 2 minus Sn minus 1 plus 1 less than or equal to R to the power of n minus 1 modulus S2 minus S1. So solve all the operation that are related to the n, and we will get modulus Sn plus 1 minus Sn less than or equal to R to the power of n minus 1 modulus S2 minus S1. Hence, lemma 1 is proven.
Okay, next I will explain about task 4. Before that, I will introduce myself. My name is Nurullah Ayuni binti Abu Jamil, and my matrix number is 203854. Okay, the question for task 4 is to prove theorem 1, which the theorem is if the sequence of n from 1 until infinity is a constructive sequence, then the sequence is Cauchy sequence. By showing that the limit of n until infinity for a modulus Sm minus Sn equal to 0, and hence the sequence is Cauchy sequence. Okay, we will start this solution by a statement, which the statement is the sequence of a real number is called constructive if there exists a constant c with the constant, the value of the constant is from 1 until 0, such that modulus Sn plus 2 minus Sn plus 1 less than equal to c modulus of Sn plus 1 minus Sn. So now suppose the sequence is constructive, which the equation contain of constant that has a value between 1 until 0. So we assume that the equation, the sequence is constructive. So next, to show the sequence is indeed Cauchy sequence, first we need to let epsilon more than 0, and for m n is not natural number, just that m and n is less than equal to k for some reason. If for some k is also a natural number. So and the second, we need to establish a modulus Sm minus Sn less than epsilon. Okay, so next, by assuming m is more than n, we will start the equation by modulus Sm minus Sn equal to modulus Sm minus 1 plus Sm minus 1 minus Sm minus 2. The equation is continue to subtract until we get Sn plus 1 plus Sn plus 1 minus Sn modulus less than equal to From this we will apply triangle inequality. So we will get modulus Sm minus Sm minus 1 plus modulus Sm minus 1 minus Sm minus 2 plus until the end of the sequence we will get the modulus of Sn plus 1 minus Sn. So this equation will be equations 1. By noticing from the equation, we notice that the modulus of Sn plus 2 minus Sn plus 1 is less than constant modulus of Sn plus 1 minus Sn, also less than equal to constant power of 2 with modulus Sn minus Sn minus 1. So as you can see, the power of the constant is keep getting bigger. So until we will get the last sequence, which is last equation, which is less than equal to c power of constant power of n with a modulus of sequence number 2 minus sequence number 1. Okay, so because of the pattern is the first index plus exponent of c equal to n plus 2 in each case. Okay, next. Okay, that is for modulus Sn plus 2 minus Sn plus 1 less than equal to Sn modulus of sequence number 2 minus sequence number 1. Okay, thus we can get bounds of summation from inequality number 1 from equation inequality number 1 that we get before, which is this equation. So we take the equation and we will get this. So modulus Sm minus Sm minus 1 equal to modulus of Sm minus 2 plus 2 minus Sm minus 2 plus 1, which is less than constant of power with power of m minus 2 times modulus of sequence number 2 minus sequence number 1. So when you keep doing the sequence of these equations until last you will get equations with modulus Sn plus 1 minus Sn equal to modulus of Sn minus 2 plus minus 1 plus 2 minus Sn minus 1 plus 1, which is less than equal to the constant with power of n minus 1 with times modulus of sequence number 2 minus sequence number 1. So we continue the solution, which give the modulus of Sm minus Sn less than equal to modulus sequence of number 2 minus sequence number 1 times with constant with power of m negative minus 2 plus with constant with power of m minus 3 plus until the end, which we will get the constant with power of n minus 1. So this equation will be equal with the second equation, which is modulus S2 minus S1 times with constant. You will factorize the equation, then you will get the constant with power of n minus 1 times with constant n minus 1 plus constant power with m minus n minus 2. Last until the end, you will get 1. So, you simplify the equation until you will get the constant power with n minus 1 times with 1 over 1 minus c times with modulus of sequence 2 minus with sequence 1. So, we will take the equations. We will put in limit equation of limit from n until infinity. So we take the equation, we will get 0. Since the limit of n until infinity for equation Cn is 0, thus this sequence is Cauchy sequence. That's all for me. We proceed to next questions. Thank you.
My name is Naizati Mati Mustafa and my metric number is 200879. I will continue the presentation with task 5 to prove lemma 2, which is any Cauchy sequence is convergent. For the solution, we let an be a Cauchy sequence and we know every Cauchy sequence is bounded. And it follows that an has a convergent subsequence a and I which is convergent to their limit. Then by definition, given epsilon is greater than 0, there exists n1 such that r is greater or equal to n1. And we have a and I minus their limit is smaller than epsilon over 2. And there exists n2 such that m and n is greater or equal to n2, and we have an minus an is smaller than epsilon over 2. Then we take this m and n is greater or equal to n, and we have an minus an, and we minus ani and add the ani to this equation, and we have an minus ani plus ani minus l. From this, we have am minus ani plus ani minus the limit. As we know, am minus ani is equal to epsilon over 2, and ani minus the limit is also epsilon over 2. So epsilon over 2 plus epsilon over 2, we have equal to epsilon. Therefore, am minus an is smaller than epsilon. Hence, every Cauchy sequence is convergent.
Okay, so now we will discuss task 6. Given theorem 2, any contractive sequence is convergent. In task 6, we need to prove theorem 2. Okay, now we need to prove the sequence to be Cauchy, that's convergent. Let x equal to xn be a contractive sequence such that all n is element in natural number. So, we know this is Cauchy sequence in general form. Now, we let epsilon more than 0 be given. Consider m and are element in natural numbers such that m is more than n. Then, we can evaluate this form and relate the general form with the triangle inequality here. Triangle inequality here. Then we get this. So now, limit c power n approach to 0 and it is element in natural number such that absolute value c to the power of n minus 1 is less than epsilon. Thus, xn is Cauchy and convergent. So, we can conclude that any contractive is convergent too. That's all from me.